Hey everybody, welcome back to my channel. This is WireDogSec, back with another video for you guys. In today's video, we're going to continue on with the pre-security room. We're in the network fundamental section here, and we're going over this room called packets and frames. Understand how data is divided into smaller pieces and transmitted across the network to another device. Hopefully you're having an awesome day today, and without further ado, let's go ahead and jump into it. Hey everybody, just a quick little blurb here. As you can see here, most people that view my channel are not subscribers. If you're new here, please consider subscribing to the channel. If you're enjoying the video, please consider hitting the like button. It helps get me in the algorithm, helps spread the good word out there, helps bring more people and increase our glorious community here. All right, I'm all about helping out others. I know what it's like to come up in cybersecurity or even try to get into cybersecurity and not knowing where to look. I'm just having this channel up so I can help out other people. All right, that's all I got. Task number one. What are packets and frames? Packets and frames are small pieces of data that, when forming together, make a larger piece of information or message. However, they are two different things in the OSI model. A frame is at layer 2, the data link layer, meaning there's no such information as IP addresses. Think of this as putting an envelope within an envelope and sending it away. The first envelope will be the packet that you mail, but once it is opened, the envelope within still exists and contains data. This is a frame. This process is called encapsulation, which was discussed in Room 3, the OSI model. At this stage, it's safe to assume that when we are talking about anything IP addresses, we are talking about packets. When the encapsulation information is stripped away, we're talking about the frame itself. Packets are an efficient way of communicating data across network devices, such as those explained in Task 1. Because this data is exchanged in small pieces, there's less chance of bottlenecking occurring across the network than large messages being sent at once. For example, when loading an image from a website, this image is not sent to your computer as a whole, but rather small pieces where it is reconstructed on your computer. Take the image below as an illustration of this process. The cat's picture is divided into 3 packets where it is reconstructed when it reaches the computer to form the final message. And you see there in the little graphic here, you got packet 1, 2, 3, and then final is complete. And let's continue on here. Packets have different structures that are dependent upon the type of packet that is being sent. As we'll come on to discuss, networking is full of standards and protocols that act as a set of rules for how the packet is handled on a device. With the internet predicted to have approximately 50 billion devices connected by the end of 2020, things quickly get out of hand if there's no standardization. Let's continue with our example of the Internet Protocol. A packet using this protocol will have a set of headers that contain additional pieces of information to the data that is being sent across the network. Some notable headers include, it has them listed out here, you got the time to live. This field sets an expiry timer for the packet to not clog up your network if it never manages to reach a host or escape. Checksum. This field provides integrity checking for protocols such as TCP, IP. If any data is changed, the value will be different from what was expected and therefore corrupt. Source address, the IP address of the machine that the packet is being sent from so that the data knows where to return to. And then we've got the destination address, which is the opposite. The device's IP address the packet is being sent to so that the data knows where to travel next. And let's answer some questions below. What is the name for a piece of data when it does have IP addressing information? Remember, that was a packet. So let's go ahead and type that in here. There we go. And what is the name of a piece of data when it does not have IP address information? Remember, that's frames, right? The data link layer. There we go. Just looking for frame. There we go. All right, task number 2 here. And let's see here. TCP IP, the three-way handshake. TCP, or Transmission Control Protocol for short, is another one of these rules used in networking. This protocol is very similar to the OSI model that we have previously discussed in room 3 of this module so far. The TCP IP protocol consists of 4 layers and is arguably just a summarized version of the OSI model. These layers are the application layer, the transport layer, the the internet layer and the network interface layer. Very similar to how the OSI model works, information is added to each layer of the TCP model as the piece of data or packet traverses it. As you may recall, this process is known as encapsulation, where the reverse of this process is called decapsulation. One defining feature of TCP is that it is connection-based, which means that TCP must establish a connection between both a client and a device acting as a server before data is sent. Because of this, TCP guarantees that any data sent will be received on the other end. This process is named after the three-way handshake, which is something we'll come on to discuss shortly. A table comparing the advantages and disadvantages of TCP is located below. All right, some of the advantages of TCP guarantees the integrity of data, capable of synchronizing two devices to prevent each other from being flooded with data in the wrong order, performs a lot more processes for reliability, and some of the disadvantages requires a reliable connection between the two devices. A slow connection can bottleneck another device as the connection will be reserved on the other device the whole time. TCP is significantly slower than UDP because of more work computing has to be done. And let's see here. TCP packets contain various sections of information known as headers that are added for encapsulation. Let's explain some of the crucial headers in the table below. And you see, you go ahead and read this yourself here. It's going to talk about the source port here. This value is port opened by the sender of the TCP packet. Destination port, it's the opposite of that. Source IP, very similar thing. The IP address of the device that's sending the packet, and destination is the opposite device that's destined for. And sequence number, when a connection occurs, the first piece of data transmitted is given a random number, acknowledgement number after a piece of data has been given a sequence number. The number of the next piece of data will have the sequence number plus 1. Checksum, the value that gives TCP integrity. Data, the headers where the data bytes of a file that's being transmitted is stored. Flag, this header determines how the packet should be handled by either device during the handshake process. Specific flags will determine specific behaviors, which is what we'll come to explain below. It says next, we'll come across or come on to discuss the three-way handshake. This term given for the process to establish a connection between two devices. The three-way handshake communicates using a few special messages. The table below highlights the main ones. All right, Step one is send. A send message is the initial packet sent by a client during the handshake. This packet is used to initiate a connection and synchronize the two devices together. We'll explain this further on. Step number two is SYNAC. This packet is sent by the receiving device server to acknowledge the synchronization attempt from the client. Number three is ACK. The acknowledgement packet can be used by either the client or server to acknowledge that a series of messages packets have been successfully received. Number four is data. Once a connection has been established, data such as bytes of a file is sent via the data message. Fin, this packet used to cleanly, properly close the connection after it has been complete. And then you got the RST, which is reset. The packet abruptly ends all communication. This is the last resort and indicates that there's some problem during the process. For example, if the service or application is not working correctly, or the system has faults such as low resources. The diagram below shows a normal direct handshake process between Alice and Bob. In real life, this would be between two devices, right? Alice, right, sends a send to Bob, Bob sends a send ACK back to Alice, and then ACK back to Bob. Their direct handshake. All right. Any sent data is given a random number sequence and is reconstructed using this number sequence and incrementing by 1. Both computers must agree on this same number sequence for the data to be sent in the correct order. This order is agreed upon during these three steps. You got send client. Here's my initial sequence number to synchronize with. Send ACK. Step number 2, server. Here's my initial sequence number to synchronize with, and I acknowledge your initial number sequence. ACK client. Acknowledge your initial sequence number of whatever. Here is some data that is my ISN plus 1, 0 plus 1. All right, and it's got another table here talking about device, initial sequence number, basically everything we just went over here. All right, and let's go ahead and continue on here. TCP and closing, TCP closing a connection. Let's quickly explain the process behind TCP closing a connection. First, TCP will close a connection once a device has determined that the other device has successfully received all of the data. Because TCP reserves system resources on the device, it is best practice to close TCP connections as soon as possible. To initiate the closure of a TCP connection, the device will send a FIN packet to the other device. Of course, the TCP or with TCP, the other device will also have acknowledged this packet. Let's show this process with Alice and Bob shown previously, right? You get Alice, Finn to Bob, ACK, Finn, and ACK. In the illustration, we can see that Alice has sent Bob a Finn packet because Bob received this. He will let Alice know that he received it and that he also wants to close the connection using Finn. Alice has heard Bob loud and clear and will let Bob know that she acknowledges this. What's the header in a TCP packet that ensures the integrity of data? And that was, let's see here, that was the checksum, right? Yeah, that is the checksum. So I'm going to type that in here. Checksum. Okay, provide the order of a normal three-way handshake by comma. Okay, remember that was it was syn, then syn ack, and then ack is the last part of it. There we go. Now let's continue on to task number 3 here. And let's see. Practical handshake. Help Alice and Bob communicate by reassembling the TCP handshake in the correct order in the static lab attached to the task. Enter the value of the flag. All right, so let's go ahead and view site, see what we can do here. All right, can you hear me, Bob? Finn, goodbye. Ack, what? All right, well, we already know it's going to be Sin, right? And this is going to be Sin Ack. Yes, I hear you loud and clear. And the last one's going to be Ack, right? I can hear you. Okay, great. All right, and let's see here. What is this? All right. And I can hear you. And all done. There we go. Awesome. See, there we go. We just basically did what they already explained there. So go ahead and hit submit here and close out of here. Go down to and continue on to task number 4. We're going to talk about UDP IP. It says the user Datagram protocol, UDP, is another protocol that is used to communicate data between devices. Unlike its brother TCP, UDP is a stateless protocol that doesn't require constant connection between the two devices for data to be sent. For example, the three-way handshake does not occur, nor is there any synchronization between the two devices. Recall some of the comparisons made about these two protocols in Room 3 OSI model, namely UDP is used in situations where applications can tolerate data being lost, such as video streaming or voice chat, or scenarios where an unstable connection is not the end all. A table comparing the advantages and disadvantages of UDP is below here. And here are some of the advantages. UDP is faster, leaves the application to decide if there's any control over how quickly packets are sent. UDP does not reserve a continuous connection. And some of the disadvantages, UDP doesn't care if the data is received or not. Remember, it's fire and forget. It is quite flexible to software developers in this sense. This means that unstable connections result in a terrible experience for the end user. As mentioned, no process takes place in setting up a connection between two devices, meaning that there's no regard for whether or not data is received, and there are no safeguards such as those offered by TCP, such as data integrity. UDP packets are much simpler than TCP packets and have fewer headers. However, both protocols share some standard headers, which are what is annotated in the table below here. You got TTL, so it's time to live. All right, you got source address, destination address, source port, destination port, and the data. All right, let's continue on here. Next, we'll come on to discuss how the process of a connection via UDP differs from that of something such as TCP. We should recall that UDP is stateless. No acknowledgement is sent during a connection. The diagram below shows a normal UDP connection between Alice and Bob. In real life, this would be between two devices. And here you go here. You request, response, response, and response. All right, what does UDP stand for? All right, I'm just going to copy and paste it from up above. Here, the user data gram protocol. All right, go ahead and grab that, plug it in here. And remember, it's a stateless connection, so let's go ahead and put that in there. Stateless. And what protocol would you use to transfer a file? And that's going to be um, TCP, right? Because you don't want half a file, as we explained in the other video. What protocol would you use to have video call? And remember, voice chat, video call, streaming service and stuff, that's going to be UDP. All right, and let's go ahead and continue on to task number 5 here. So task number 5, Ports 101, Practical. Perhaps aptly titled by their name, ports are an essential point in which data can be exchanged. Think of a harbor and port. Ships wishing to dock at the harbor will have to go to a port compatible with the dimensions and the facilities located on the ship. With the ship lines up, it will connect to a port at the harbor. Take, for instance, what a cruise liner cannot dock at a port made for a fishing vessel and vice versa. These ports enforce what can park and where. If it isn't compatible, it cannot park here. Networking devices also use ports to enforce strict rules when communicating with one another. When a connection has been established, recalling from the OSI model's room, any data sent or received by a device will be sent through these ports. And computing ports are a numerical value between 0 and 65,535. Because ports can range from anywhere between 0 to 65,535, there quickly runs the risk of losing track of what applications using what port. A busy harbor is chaos. Thankfully, we associate application software and behaviors with a standard set of rules, for example, by enforcing that any web server or web browser data is sent over port 80. Software developers can design a web browser such as Google Chrome or Firefox to interpret the data the same way as one another. This means that all web servers now share one common rule: data sent over port 80. Now the browsers look, feel, and easy to use is up or yeah, easy to use is up to the designer of the application or user's decision. While the standard rule for the web data is port 80, a few other protocols have been allocated a standard rule. Any port that is within 0 to 1024 is also known as a common port. Let's explore some of these other protocols below. All right, it goes in and talks about these common ones out here, right? You got FTP, file transfer protocol on port 21, for use of file sharing, client server model, SSH, port 22, use to securely log into systems, HTTP, port 80, www, right? You're browsing the web in your web browser, unsecure, unencrypted, HTTPS 443, it's encrypted traffic using a web browser, right? And SSB, secure message block 445. This protocol similar to FTP, however, as well as files SB or SMB allows you to share devices like printers, and you got RDP 3389. This protocol is secure, meaning of logging into the system using a visual desktop surface or interface as opposed to text-based limitations, right? You'll see that on Windows boxes, right? And then let's continue on here. We have only briefly covered the more common protocols of cybersecurity. You could find a table of the 1024 common ports listed for more information. What is worth noting here is that these protocols only follow the standards, i.e., you can administer applications that interact with these protocols on a different port other than what the standard running a web server on port 8080 instead of port 80 standard port. Note, however, applications will presume that standard port is being followed, so you will have to provide a colon along with the port number. That's absolutely true. All right, now we're going to get into the practical challenge. Just open the site attached to this task and connect to the IP address 8.8.8.8 on port 1234, and you'll receive a flag. So let's go ahead and do that here. Open up this um, little browser here, and it wants us to connect to 8.8.8. So let's go ahead and type that in here. All right, here we go. And it says 1234 for the port, right? And NC is netcat, by the way, for y'all that don't know. Letting it connect here. There we go. So I'm going to go ahead and copy this out and paste it in. And let's continue on here to this last piece. All right, task number 6, continue your learning, extending your network. Join the final room of this networking module, extending your network to continue your learning and complete this module. All right, now if y'all enjoyed this video, if you found it informative, and you're new here, please consider hitting that subscribe button with the notification bell so you know every time I post. Hit the comment section below your thoughts and opinions. All right, we're trying to start a community here, guys, so be sure to Ask questions if you're curious about things, maybe share some knowledge, some tips, tricks, what have you, and hit that share button, share with your friends, whatever. And as always, thank you for watching. Have a nice one, and I'll see you later.